In this next part of the course, we're going to talk about sets and quantifiers. Within the section, we're going to learn what a set is and when it is such a fundamental structure within mathematics. We're going to work with the different set notations and explore operations on sets. We're going to work within Venn diagrams. Some of you might have seen them before. And then we're going to prove laws and various ways to approach sets and proofs on sets. Then we're going to move into the quantifiers. Universal and existential quantifiers will correspond to statements that are for all, universal, or there exists, existential. And these are going to be very useful within the mathematical proofs that we're going to talk about later in the course. We're going to see how to actually decipher statements with multiple quantifiers. There exists something so that for all of these and so on. And we're going to talk about the negations. Now, thinking about sets is actually quite intuitive. Let's start by thinking about numbers. Any child will be able to tell you the numbers in a list, 1, 2, 3, 4, 5, and so on. It's kind of like a rhyme. But we can think of counting numbers in two different ways, as a list, the way a child does when it first learns it, or as a set. So all of these numbers in a collection, in a bag together with no particular order imposed on them. The list starts with one and carries on. The set is simply a collection of these that are not ordered. So in terms of my apples pictures here, I can think of these apples as being in a line and therefore as a list in a particular order, but I can think of a bowl of apples in no particular order whatsoever. As long as I know that a certain apple is in the bowl, that is basically all that is important. There are a number of different ways to describe a set. We can use a verbal description, for example, the set of primary colors. We can specifically list all the things that go in a set. We call those elements. Within the curly brackets, I know that this is going to be a challenge to draw them in any kind of reasonable form by hand. Anything that resembles a curly bracket is good enough. And there's also a set builder notation that is mathematically useful that we're going to explore in a little bit more detail shortly. Normally, we give sets names so that we can refer to them easier later on. And normally, although it doesn't have to be the case, they are capital letters. The first piece of notation here that we're going to see is this symbol here. It means that something is an element of the set, whereas the crossed out version of it means something is not an element of the set. So let's take a look at these sets here. I'm going to, for example, give this guy a name A. So my set A consists of 3 elements that are primary colors, red, yellow, and blue. And then I can already start making statements about whether or not something is an element of the set. So for example, is it the case that red is an element of set A? So this is literally read as is an element of or is in. So is it true that red is in set A? Well, yes, it is. I can see it right here. So that is, of course, correct. What kind of statement can we make about something not being an element of set A? Well, I can, for example, see that purple, which you can see is my favorite color by the pen that I'm using, is not an element of A. It does not appear in this set here, and therefore it is not an element of. There are 2 very important nuances when it comes to sets that we're going to see as we work with them. First of all, as already mentioned, the order does not matter. How the apples or how the colors appear here does not matter within the set. So you notice already that when listing elements, we don't actually care where in the set it appears, as long as it either appears or it does not. And we will also ignore any kind of repeats. So I don't include, for example, red here twice. If it's already in there, then it's already an element. Any kind of repetition is going to be ignored. One very special set that arises in sort of edge cases within mathematics, and it's very important, is called an empty set, and we denote it with this symbol. So a circle or a 0 crossed all the way across. So this is also a heads up. If you generally write your zeros with the cross in the middle, for this section you will have to drop that notation because a circle or a 0 crossed out will specifically represent the empty set that is very not much the same at all as an actual element that is a number 0. The way to think about empty set is basically within the same bowl analogy. These braces, when you think about representing elements of the set, represent the boundaries of the bowl. So this essentially said that you have yourself a bowl with 3 colors, red, yellow, and blue inside of it. I know that colors are an abstract concept, but bear with me here. You can think of these braces as being your bowl or a bag of some sort. An empty set is just an empty bowl, but it is a bowl. So you still have that abstraction, you should still have that abstraction in your head. That empty set doesn't mean that there's nothing at all. An empty set means that you have yourself a bowl, it's just it happens to be empty. Because we're going to be working with numbers, there are a number of different shorthands that we use for frequently seen sets. For example, this bold letter R denotes a set of all real numbers. The bold letter Q denotes a set of all the rational numbers, so numbers of the form A over B, where the bottom is not 0. The Z, the bold letter Z, represents sets of all integers, so all the counting numbers, all the negative counting numbers, and 0. And N represents a set of all natural or counting numbers. The way that we write these letters by hand as opposed to typed is going to be to double up on one of the sides of the letter, generally the straightest side, or just one of them. So for Q, we're going to double up on that and write it like this. For Z, we're doubling up on the diagonal, and same for N, we double up on the leftmost part. And then we're also going to see the variance of each one of these. If you have a plus on the top, that refers to the set of all the real numbers that are greater or equal than 0. So let's write that down. R minus, this minus should be in the exponent, represents the set of all the integer or of all the reals that are less than or equal to 0. So the 0 will actually be included in all of these, in both of these. The reals with the non-negative on top represents the set of all the reals that are strictly greater than 0. So if you think of a number x as a general representative of a set R plus here, then x has to be greater or equal than 0, where if you think of a representative of a non-negative set, then it has to be strictly greater than 0. 0 is no longer allowed to be in the set. And the set that is denoted by R star will represent all the real numbers except for 0. So it's everything but 0. Now I'm saying that these are variants of each because these superscripts can appear on any one of these sets and actually have the same meaning. So Q plus will represent of all rational numbers that are greater than or equal to 0. Z minus will represent all the integers that are less than or equal to 0, and so forth and so on. Let's think about how we're going to write out our sets. So, as we already seen before, we can provide a verbal description, we can list all the elements within the brackets, or we can have this set builder notation, and then we will see which one is more useful when. So here, I am given a verbal description for 2 different sets. Specify a set of all integers between 1 and 5. Okay, so integers between 1 and 5, I can actually write that out. 1, 2, 3, 4, 5. Excellent, that's another way to actually write out my set in very explicit, very direct form. What about the next one? Specify a set of all reals between 1 and 5. The real numbers include all of the possible fractions and all of the possible rational and irrational numbers in between. So if I start writing this out, well, 1 has to be the smallest, but I immediately know that I'm in trouble because there's no way I can possibly list all the possible real numbers. What am I going to do? Like 1.1, 1.05, 1.0001, square root of 2, and so on, right? Like there are, in fact, infinitely many real numbers between 1 and 5, so I can't possibly list them all. What do I do? This is where the set builder notation comes in handy because it allows us to specify what the elements of a set are without actually listing all of them. This is normally what the set builder notation looks like. We're going to make a statement about a general representative of a set, S. So in this case, we're going to say that this part represents, if you're going to read it out in English, it will say all elements in S. So once again, this X serves as a representative, a very general representative of an element that is within S. This vertical bar is read as a statement such that. So this is literally just a shorthand, a mathematical shorthand for the words such that or so that. And then this last part, P of X, represents some kind of property that we want all of these elements to actually have. So property P of X is somehow satisfied. So it's called a set builder because I am literally building my set out of the elements in S such that a certain property is actually satisfied by all of them. Let's practice this new notation with a bunch of these examples. So first, I'm going to go back to the two that I've already seen before, a set of all integers between 1 and 5. So looking at this, I need a representative of a set of integers. So I'm going to start with X is an element of the integer set. I'm using my integer notation that I've also just introduced on the previous page, such that, and what is the property that I want these integers to satisfy? Well, I want these integers to be between 1 and 5. So that I can accomplish by writing down the inequality that these integers actually have to satisfy. Okay, so now I can read this throughout. This is a set, because I have curly brackets, of all the integers that are between 1 and 5. Again, remember that this X is just your generic representative. There is nothing particular about X. It actually varies to be whatever you want it to be, but it has to be an integer such that it is between 1 and 5. So what about this second part that we were unable to do on the previous page, simply because we can't possibly list all the possible real numbers between 1 and 5? So in this case, my set builder will be, these are the elements within the real numbers such that this element is between 1 and 5. Okay, does that look reasonable? Is there anything else that we can say here? Set builder notation is usually pretty straightforward, but you do have to get a hang of how to use it if you're giving the verbal description first. Let's see what the other questions are asking here. How many elements are in this set? Remember, the elements are all of the pieces within this collection of the objects. So what are the elements in the set? Well, I can see 0, I can see 1, and I can see 2. So there's 3 elements all together. How many elements are in this set? Remember that we are going to ignore the repeats within the set, because once an element is in, we consider it to be in. We don't need it to be repeated, which means that we're going to ignore these last 2's as completely redundant. And therefore, the number of elements in this set is still 3. When you're counting the number of elements in the set, they have to be distinct. Let's talk about this nuance. How do we compare an empty set to a set containing an empty set? So as we just discussed on the previous page, the empty set itself is like an empty bowl. You just have yourself a bowl, no apples. So this is what this is. What about this guy? It's a set, which already is a bowl, containing an empty set, which is an empty bowl. So this set is going to be a bowl inside a bowl. They're both empty. There is no apples in it, but I do have myself 2 different bowls. This one is just an empty bowl, and this one is an empty bowl within an empty bowl. Okay, so just because it's an empty set, a set containing it isn't also in itself empty. Pause it here for a second and really try to picture those bowls so you can see the difference between an empty set and a set containing an empty set. How about this? How many elements are in here? You notice that I have lots of brackets going on, and I'm going to have to try really hard in order to think about what is contained within this biggest, farthest sort of away set. Let's maybe highlight these elements. So I can see that my first element is just this one here. My next element is a set containing 1. And my next element is a set containing 1 and a set containing 1. So altogether, I still have 3 elements, although they are nested sets within themselves. This largest set contains 3 pieces. The pieces are a little bit more complicated than just straight up numbers, but they're still just 3 main pieces within this set. The first sort of operation that we're going to define in a set, or something that will allow us to talk about sets a little bit differently, is the notion of being a subset. So if I have 2 sets, A and B, A is called a subset of B if and only if every element of A is also an element of B. And this is how we write it. So A is contained within B. This symbol should be reminiscent of the less than or equal to, but we can't compare sets the same way we compare numbers. So for example, I can say that 5 is less than or equal to than 7 because, well, for many reasons. 5 apples is fewer than 7, 5 comes first on the number line before 7, and so on. If I have a set, I can't say it's less than or equal than, let's say, 2, 4, 6, because that is meaningless. There is no comparison in terms of the actual magnitude of a set. The best I can do is think about what does it mean to be contained within. So the subset of a set will be some sub-collection of its elements. And that is what this definition actually says. A is a subset of B if every element that I can pick in A is also going to lie in B. Now, B might have more elements still, but certainly everything that is in A will also be in B. And then, as again, with the less than or equal or less sign, once we take away this equal, we take away the possibility of equality. So we call it a proper subset if they can't actually be equal. So A has to strictly lie within the actual set B. Now both of these conditions we can write out in terms of the logic statements that we've used before. We can translate a little bit into already familiar language. So again, picking a generic representative, let's call it X, and that will represent every element of A. What this is saying is, if X is in A, then X is also in B. Right? For every element in here, once it's in here, it means that it's also within B. Whereas for the proper subset, I must have that it's first of all a subset of B, but also, and this is going to be an and, it cannot in fact be equal to B. It has to be sort of strictly contained within B. I know that this is still a little bit abstract because we're dealing with sets that we don't have a particular handle on. So let's take a look at a very particular set, a set containing elements 1, 2, and 3. And let's list all the possible subsets of it. So what are the sets that lie within it? Well, I can start, for example, with just 1. The set containing 1 is a subset of this set. And let's make sure that it's not just our intuition that suggests that, because we can clearly see that 1 sort of fits in there and then there's some other stuff. Let's make sure that it actually follows the definition. Every element of the subset is contained within the larger set. Is that true? Well, certainly there's only 1 element here, and it is in fact here. The next subset I can have is a subset containing just 2, and the next subset I can have is just a subset containing the 3. So I can have these sort of like singleton subsets. What else is a subset? What if I have 1, 2? Is this a subset of that? Well, I can see that 1, 2 lies within it. So yes, that is a subset. And that way I can go through all of the subsets of size 2 and list them all. Am I done in terms of subsets here? Well, remember that subsets mean that it can in fact be equal. So the entire set, 1, 2, 3, is in fact a subset of itself. Because as per the definition, every element of a subset is an element of the larger set. And in this case, quite literally, every element is in there and nothing else is in there. Are we done yet? Do we have any other subsets of this set? Well, again, let's think about this as a bowl. So I have myself a bowl and I have elements 1, 2, and 3 in this bowl. And a subset is if I take the elements out and then I sort of start filling in the bowl. I can throw 1 in, and that's the subset that contains just the element of 1. If I throw in both 1 and 2, then it's a subset that contains both elements 1 and 2. And so I seem to have accounted for all the possible ways I can go about filling in the bowl except for one. What if I don't throw anything into the bowl at all? My elements 1, 2, and 3 can stay out here, and the bowl can stay empty, and that will still be a subset of the original set. So the one set I'm going to list, and I'm going to list it in the beginning because it's the smallest one, is going to be the empty set. Okay? So in terms of proper subsets, I can actually see that all of these guys, except for the full set itself, are proper subsets of the original set. Okay, so proper means it can't actually be equal, but all the other ones that are smaller are proper subsets of it. So if we have 3 element set, how many subsets did we actually come up with? 1, 2, 3, 4, 5, 6, 7, 8. A 3-element subset has a 3-element set has 8 different subsets. Okay, let's go through a few examples so we can see how else we can use these types of notations and how we can think in terms of subsets. I have sets A, B, C, and U here. So U normally stands for the universal set. So these are essentially all the numbers that I'm going to be thinking about, and all of these other sets somehow live inside of this universal set. Is it true or false that 4 is an element of A? Yes, it's right here, so this is true. Next up, maybe I should pause here and say, really pause the video and try this for yourself, and then come back to go through this with me. Do that and come back to me. Okay, so on to part B. Is it true or false that 3 is an element of B? Is 3 an element of B? Yes, there it is. So this is true. Is it true or false that A is a subset of B? So again, as per our definition, that means that every element of A has to be inside of B. Is that true? Does A fit inside B? No, we can see that right away. There's a number of elements in A that are not in B. So for example, 1 and 2 and so on. So this is false, and you can even give it a counterexample to prove that you're right in saying that it's false. 1 is an element of A, but 1 is not an element of B. Is it true or false that B is a subset of C? So B somehow fits inside C? No, we can see that that's still not true because, for example, 4 is in here, but 4 is not in there. So this is still false. Is it true or false that B is a subset of the universal set U? Well, yes, that looks like it's true because all of the elements of B are in fact between 1 and 15, which we assume this to mean. So side note here, this is notation I have not yet introduced. The ... Normally, when we deal with sets that we would like to write out explicitly the elements of, but there's still a little too many to bother, we say ... assuming that a pattern that we have envisioned holds between the elements that we do list. Given the fact that everything else here is an integer, I simply assumed that this is a set of integers between 1 and 15. For the next example, we have that B is given to us with a set builder notation, and C is just a set of 3 elements here. So let's see, what is this builder notation telling us? B is a set of integers that are between -10 and 10. So if I wanted to write this out, I would be able to actually write out all of the elements of B because they're integers, between -10 all the way up to 10. Now let's go through these and see which ones of them are true and which ones are false. Again, pause here so that you can try this for yourself. Is it true that C is a subset of B? So does C fit inside of B? We can see it here that yes, for every element of C, it does belong to B, so this is true. Is it the case that B is a subset of C? So does B fit inside C? We can see very clearly that that's not true because B in fact has a lot of elements that do not appear in C. So this is false. Is it true that B is a subset of the integers? Yes, it's true by definition. We're actually picking specifically from integers that also have this additional property. So this is true. Is B a subset of positive integers? No, that's not the case. We see that there is a lot of negative integers in B, so this is not the case. Is C a subset of rational numbers? Are these all rational numbers? Well, they're integers, but integers in particular are rational numbers because we can picture them as having denominator 1, so that is the case. Is C a proper subset of the integers? So proper means it is a subset, but it is not equal to. And that is the case. This is a subset of the integers. It has some of the integers, but it certainly doesn't have all of them. So it is a proper subset of the integers. Is C a proper subset of C? So is it a proper subset of itself? Well, no, because it fits within itself perfectly and therefore is equal. So it's not, while it is a subset of itself, it is not proper. So is this statement true? Is C a subset of C? Is it true that every element of C lies within C? Yes, that is in fact true. So it is a subset, but not the proper type. Another set that is useful to have is a power set, and we denote it with this kind of script P. So for any set A, the power set is the set of all the subsets of A. Let's take a look at the example. So we start with the exact same set we've seen before, and we've already listed all of the subsets of it here. So I'm going to cheat a little bit and take all of these guys and actually list them here again. So for all of the subsets of the set 1, 2, 3, we have these guys. Now, for the actual power set, let me make this a little bit smaller. Notice that a power set is a set containing all of the subsets of A, which means that I have to include all of them within the extra set of brackets, indicating that I now have myself a bowl containing all of these smaller little bowls. What about the power set of just 1, 2? Well, we can proceed in a similar fashion to how we found the subsets of 1, 2, 3. So the smallest thing I can do is include the empty set. Then I have a set containing just 1, a set containing just 2, and a set containing both 1 and 2. And the power set will have to contain all of these. What about a power set for the set containing just the 1? Well, I can once again, I'm gonna get a little off the line here. I can once again start with an empty set. So I start with an empty bowl, that's a subset, and then I have to start putting elements in it, but there's only 1 element to put into my bowl. Once I put in the 1, that's my entire set. So the power set of the set containing 1 single element is just these guys. What about the power set of the empty set? what are the potential subsets of the empty set? Well, the empty set only has one subset, and that is itself. So this is only going to have one subset, itself, but because I am writing a power set, I have to include it within its own brackets. So the power set of an empty set is a set containing the empty set. So just to once again highlight the notion of what a power set is, you start yourself with a set, and you start yourself with the set outside of your bowl. And then you try to fill that bowl with all the possible combinations of all of these elements. And what now happens to be within the bowl is actually your power set. So these outside brackets are your power set bowl containing all of the possible smaller bowls composed of the elements of the given set. So this one in particular, because that seems to be a little bit trickier, the power set of an empty set, so the power set of just an empty bowl is a bowl containing it, right? So I have put my empty bowl inside another bowl so that my new larger bowl has all the possible combinations of the elements that I started with. Funny story here. When I was a grad student, we played in the volleyball team, and we called ourselves the power set. Power set, volleyball, set, get it? And being math nerds, of course, we decided that we were going to decorate our t-shirts with the numbers that corresponded to a power set of something. There were originally 8 of us, which is exactly how many elements there are in the power set of the set 1, 2, 3. So this seemed to be quite perfect. And then one more person joined and we were in trouble because it's not like you can change the power set. These are what they are. So our solution to the problem was to say that our one different element is actually going to be the set containing the empty set. And while that's not in the exact same power set here, I was actually happy to take that t-shirt. So this was in fact my t-shirt number on the power set volleyball team at UVic. The next topic we're gonna talk about are the operations on sets. And you will hopefully recognize some analogies to the things that we have already seen previously in this course. In order to operate on sets, we're going to, first of all, think about what we can do with 2 different sets. If I start with A and B as sets, the union will consist of all the elements in A or B. I'm going to denote the union with this symbol, and this is kind of reminiscent of a letter U for the union, so it's easy to remember. This is what we write in how the union is composed in terms of a set builder notation. So these are the elements in the universal set such that either it's an element of A or it's an element of a set B. So the union is going to the representation of all the elements together. The next one is the intersection. The intersection, denoted by this sign, consists of all the elements such that they are both in A and they are in B. So they have to be common to both the elements. And this is what generally the intersection actually corresponds to. Common elements between the 2 sets. And then the final operation for now is going to be called the complement, and that consists of all the elements not in A. So all of the elements in the universe that are specifically not in A. So everything outside, let's say, of A. Do these 3 operations remind you of some other operations that we have seen in this course so far, especially in terms of their connectives, or, and, not? This is very analogous to the logical operations that we have seen, right? In fact, if you really want, you can use a shorthand for or and a shorthand for and here, and the complement, well, we can't say quite not in A because A is not a proposition, but it's the exact same feeling. It's everything that is not in A. For the complement in particular, I should point out that there's a couple of ways that the notation will work. So we're going to be using the letter C, which stands for complement. But a lot of places in the literature use the over bar here. So this is going to represent not A. And this is maybe a little bit more similar than to the same logical and analysis own. Let's take a look at how this works in examples. So my universal set are the integers between 1 and 9. My A is 2, 4, 6, 8, B is 2, 3, 5, 7, and C is 1, 3, 6, 9. And let's actually apply these newly defined operations to these sets to make sure that we understand how they work. I encourage you here to pause the video and try this for yourself. These operations are fairly straightforward. It just gets a little bit of practice to make sure that you got them down. Okay, so first up is the complement of A. Remember, it's everything outside of A, everything inside the universe that is not an A. So this will be the set containing the elements that are specifically not contained in A, but are contained in U. So 1, I can't include 2 because it is an A. The next one will be 3, 5, 7, 9, 10. By the way, I am not infallible, so if I made a mistake somewhere, please make sure you actually let me know so I can correct it. And don't think that every single little bit that I say is always correct. I could easily have accidentally omitted an element here and not noticed it. Next up, A union B. So the union corresponds to all the elements being all together. So that means that I'm going to take everything in A and everything in B and unite them within this new set. So everything in A, and I might as well start writing them all down. Remember, in the sets, order does not matter. So I can start with all the elements of A and then throw in everything from B. So everything else from B. Well, if I include 2 here again, then I will be repeating the 2. It's already there. There is no need to include it. Remember that repetitions are going to be ignored. So I'm going to skip the 2 as already being present. And then I am going to include the rest of the elements of B. 3 hasn't appeared yet, 5 hasn't appeared yet, and 7 has not appeared yet. And there we go. All right, next up is A union B complement. So as before, when we were talking about logic, and as it is always within arithmetic, we respect the brackets. So that means that we have to do whatever operation comes in the brackets first, and then everything else. A union B is this set right here, and then we need to apply complement to that. So that means that I'm looking at the complement of this set. So all of the elements that are not in this, but are in my universe. What are those elements? Let's see. The elements that are not in here, that are between 1 and 9, are 1. Well, actually, and just 9. Everything else is in here. 2, 3, 4, 5, 6, 7, 8 are all here. So the only elements that are not appearing in A union B are 1 and 9. Here, in the next one, I have 2 intersections, but no brackets. We're going to see later on that it doesn't really matter where you put the brackets as long as the operations are the same. Remember, again, this is similar to the logic rules of equivalence. But for now, let me just put the brackets on the first 2 sets. So A intersection B and then intersection C. This is how we're going to see that these operations can be generalized for more than 2 sets in the most natural way possible. So first, let's start by computing what I've now included inside the brackets, A intersection B. Remember that the intersection means all the common elements. So I have to think of all the elements that are common to both A and B. Let's take a look at A and let's take a look at B. What elements do they have in common? The only one that I can see that they have in common is an element 2. So that is going to be my entire A intersection B. And then I have to intersect it with the set C. Okay, and I'm going to just write it out here so I don't have to constantly be looking back up. Okay, again, I have to now apply the intersection. So what do I have in common between these 2 sets? Nothing. There are no elements in common. But remember, the nothing in the set world means empty set. The only thing that these things have in common are, in fact, the bowls. I have a bowl containing 2 and a bowl containing 1, 3, 6, 9. So the only common element in a sense. I mean, there's no elements in common, but the only common thing amongst them is the ball itself, so the empty set. Okay, proceeding in a similar fashion, we're going to do this. So now my brackets are on B complement union C, and then I'm going to have to intersect it with A. So it's going to be A intersection not B union C, which will be 1, 3, 4, 6, 8, 9. And when I intersect these two, I am going to get that the common elements are 4, 6, and 8. So I'm going to skip this one, leave it for extra practice for you, but I will go over these more conceptual ones. Now, next up, we have A intersecting not A, or A complement. Now, in this particular case, we actually have our sets written out, so we don't even have to do many more calculations. We simply have to put together the intersection. I have my set A here, and the set A complement that I computed in the very first part of this equation. Intersection signifies that I'm going to be looking for what is common to both of them. And if you look at them for just a second here, you'll notice that there's nothing in common. The intersection of these two is going to be the empty set. Now let's see if we can reason it out without even looking at the sets themselves. We have a set A intersecting with a set A complement. Intersection means we're looking for common elements. A complement means that it's everything not in A. So I'm going to think of what are the elements that are common to A and everything that is very specifically not in A. Well, they clearly have nothing in common because the complement was constructed to be everything outside of the elements of A. And therefore, it also makes sense a little more abstractly that the answer will be the empty set. What is the intersection of the set A and the empty set? So what does A, this one, or really any other, has in common with the empty set? Well, the only thing that they have in common is the empty set itself. What about this one? A union the universal set, so everything. Remember, the union corresponds to all the elements being put together. So I'm putting together everything that's in A together with everything that's already in U. Now, U is all of the possible elements that I'm considering. So A will always be consisting of the elements that are already inside the U. So this union will always produce the universal set as the result. Now, this is the way to deal with sets in this sort of procedural listing all of the elements format. The other way to think about them is a very visual representation that will come in handy for a bit more of the abstract way to approach these things. And the tool for that is called a Venn diagram. The way we start any Venn diagram is we draw a rectangle that represents the universal set, everything that we are actually thinking about working within. So we're going to start with the rectangle. So now I'm going to draw myself a circle representing elements of a set A. So what I'm going to think about is that the inside of this has a bunch of points on the plane, right? So think about like the plane, or more abstractly, just everything that is contained within this circle is actually the elements of A. If you're given a very particular set A, you can think of those elements living inside of it and only those. So in this case, it's going to be 2, 4, 6, 8. That is everything that lives inside of A. But if we're going to abstract a little bit more, we're just going to think of everything that is in here is inside the A. Now here I'm trying to draw A union B. So that means that I have to draw the set B as well. It has to be within this rectangle because that's my universal set. But what does that look like? Is my set B going to go here? Is it going to go here? Is it going to go somewhere in the middle? The most general format in which we're going to draw this set is going to be as such. So that means I will have sets, these circles intersect, not quite be within each other. This is going to be the most general form. And then if we have any additional information, we're going to adjust our drawing based on that. But this general format is going to be the most standard way of starting to draw a Venn diagram. If we are asked to represent something in particular, like A union B, we're going to shade the region that corresponds to the elements within this newly composed set. So remember that the union are all of the elements inside of both A and B. So the union will correspond to everything in A and B all together. Next up, let's draw A, B, and their intersection. So I'm going to, once again, start with a rectangle for my universal set. My rectangles are not going to be the same size, and that's okay. I'm going to, once again, produce two sets in the general position, A and B here. Make sure you label them so that you know which one is which. The intersection are the elements that are common to A and B. So it's gotta be elements that are both in A and in B. And this is also where the visual representation actually is intuitive. The intersection of the sets will be the intersection of the circles. So the region that corresponds to the common elements is where the circles overlap, right here. If we are given additional information about sets, for example, the fact that we're disjoint, we can include that in our Venn diagram. So now, instead of this general position, if I know that they're disjoint, it means that they have to not touch each other or overlap. So A and B will be completely separate circles here. Now, the next up is the complement. So once again, we're starting with a rectangle. Now, in this case, I'm drawing only the complement of A, so I only have to draw the one set A. B is not even in the picture. And the complement of A is everything that's not in A. So it's everything outside in the world that is not inside of A. So it's the region that is physically outside of A here. And finally, we are going to draw what it means to be a subset of. So I have two sets here, A and B, but I'm told very specifically that A is a subset of B. So remember what that means? Every element of A has to also be an element of B. Every element of A, so if I draw my A, so for example, this is my A, I now know that every element of A, which means this entire circle, has to lie within B. So my circle for B has to completely contain the circle for A. Notice, of course, that again, this is potentially with equalities, so this circle for A might actually contain everything inside of B as well. So maybe the only elements that occur are already all in A, and therefore these circles are actually equal, but we don't know that yet, and therefore we're going to leave this as the more general representation of the subsets. Venn diagrams are going to be useful for many reasons, but in particular, they will be helpful in visualizing various general properties of sets. So for example, let's think about what all of these are going to be equal to while imagining the Venn diagrams for them. So the first one, if A is a subset of B, then what is A union B? So A is a subset of B is this Venn diagram right here. We have A lies inside of B, so what is going to be the union of A and B? The union are all the elements within A and B all together. So my union is going to be all the elements of A and all the elements of B. So all of this. Well, A lies within B, so all I'm going to get shaded, as we can see here, is just B. And that is my conclusion to here. Now, this is not quite the proof, but it is a very strong intuition that that is what's going to be the case. Next up is the same. If A is a subset of B, the same setup, then what is the intersection? Remember that the intersection is what they have in common. So between this, all of the things inside of A and all of the things inside of B, what is the overlap? If I shade everything in A one way and I shade everything in B the other way, what are the areas that are double shaded and therefore have overlapped in the first place? Well, I can clearly see that it's actually everything inside of A. So my answer to this here will be A. A intersection not A. So I have the not A highlighted here, and I'm going to think about the intersection with A. Well, I can see that if I take everything in here and I think about what does that have in common with everything out here, it's going to be absolutely nothing. And so the answer is going to be the empty set. Then the same two sets, but a different operation. Everything in A union, so together with everything outside of A. Well, all together, that's going to give me all of the elements in the universal set. So my conclusion here is going to be U. And similarly, you can continue to fill all of these out. Think about them for a second and see if you can justify that the answers are going to be A intersection empty set is going to be empty. A union the empty set is going to be A because there's sort of nothing to be added. It's already full. And then in terms of these ones, Venn diagrams again will provide a very strong intuition for it. A intersection the universe. So if I have my universal set and I'm intersecting A with it, and I'm thinking of what they have in common, it's going to be exactly what the elements of A are. And A union, the universe, will be the universe itself.